Hello, everyone. I hope you're all safe and sound. Welcome to the 19th lecture on analog and digital electronic circuits, in which we will study BJT-based Class A and Class B output stage amplifiers. Before we get into a detailed analysis of these two different types of output stages, I will quickly go through some important design requirements on output stages as well as their classification. So the motivation behind the use of a multi-stage amplifier is the fact that a single stage cannot usually satisfy all the design requirements of an amplifier. So we cascade different stages to form a cascaded multi-stage amplifier in which each stage serves a particular purpose. So, for example, the input stage is designed to offer large input impedance to the source signal for maximum coupling of the source signal with the input of the amplifier. It is also designed to offer high noise immunity so that the effect of noise on the performance of the overall amplifier is minimized. The middle stages, they are typically the voltage amplifiers, so they provide voltage amplification. And the final stage, which is also called the output stage, is designed to have low output impedance so that maximum output voltage is coupled with the load of the amplifier. Since the output stage is the final stage of a multi-stage amplifier, it usually deals with large voltages and currents because the small signal, when it travels through the chain of amplifiers in the multi-stage amplifier, it is amplified by the middle stages before it reaches the input of the output stage. So it has already been amplified by the middle stages before it reaches the output stage. So output stage typically deals with large voltages and currents. This means that the small signal approximation is either inapplicable to the output stage, or if it is to be used, then it should be used with care because the results obtained from the small signal analysis of the output stage, they may not be consistent with the actual performance of the circuit, simply because the output stage might not qualify for the small signal analysis of the circuits. So nevertheless, linearity of the output stage remains a very important design criteria. The output stage, as is the case with the other amplifier configurations, should be linear in nature. That is, if we excite the output stage with a sinusoidal signal, then the output must be a sinusoidal signal. Only scaled version of the input, but it should be a sinusoidal signal. If the output stage is not linear, then it will produce distortion in the output. In the form of harmonics. That is, the output signal will not be just a scaled version of the input signal. It will have a different shape. So if the output signal is not sinusoidal, then from Fourier analysis, we know that if a signal is not sinusoidal, we can represent it as a weighted sum of sinusoids, in which the component that corresponds to the fundamental frequency is called the fundamental component, and that is the intended output of the output stage. That is the intended output voltage. The other components, they're called harmonics. And so if we take the harmonics out, then what we're left with is the fundamental sinusoidal component, which, like I said, is the intended output of the circuit. So those harmonics, they are the manifestations of distortion in the output. So if the amplifier is not linear, then its output will have harmonics. And the linearity of the circuit is gauged with this quantity called the total harmonic distortion, which is defined as the ratio of the square root of the sum of the square of the RMS values of the harmonics to the RMS value of the fundamental. So THD, it specifies the harmonics present in the output signal as a percentage of the fundamental component. So since the magnitude of the harmonics should be as small as possible for the distortion to be as low as possible in the output signal. THD should be small. In other words, if THD is small, then it indicates that the distortion in the output signal is low. That is, the magnitude of the harmonics is very small compared to the magnitude of the fundamental signal. So a good linear amplifier has a very small THD, very small total harmonic distortion. Another important design criteria for the output stage amplifiers is the power conversion efficiency. That is, it is the provision of the required amount of power to the load in an efficient manner. So this in turn puts a constraint that the power dissipation in the output stages should be as low as possible in order to prevent the transistors from getting damaged due to the excessive heat generated by the power dissipated. So output stages should be linear, and at the same time, they should have high power conversion efficiency. That is, the power delivered to the load should be a higher percentage of the power consumed by the output stage itself. So the power, which in turn stipulates that the power dissipation in the output stage should be as small as possible. So depending upon the biasing of the transistors in the output stage, there are different types of output stages. So the first type is called the class A output stage. And the transistors in a class A amplifier or class A output stage, they are biased at a current, at a collector current IC, which is greater than the amplitude or the peak value of the signal. That is, the peak value of the AC signal is smaller than the biasing current. So the waveform of the collector current conducted by a transistor in a class operating in a class A mode is shown in this diagram here. So you can see that the instantaneous values of the current, these values, they're always positive throughout the conduction cycle, throughout the cycle of the input signal. So in a class A output stage, the transistors, they conduct for the whole cycle of the signal current, which gives them a conduction angle of 360 degrees, as can be seen from this waveform here, because the instantaneous values of the current, it is always greater than 0 in this case. So the transistors, they conduct for the whole cycle of the input sector, and such transistors are said to be operating in class A mode. If the amplifier is output stage amplifier is biased at 0 collector current, then the collector waveform of a transistor in that output stage is shown in this diagram here. So in this diagram, you can see that the transistor is biased at 0 current, and so it only conducts during the positive or one half cycle of the input signal. In the other half cycle, it does not conduct, because transistor cannot conduct negative current, so it goes into cutoff. So such output stages which are biased at 0 collector current or at 0 current, they're called class B amplifiers. So they're called class B output stages. And the transistors operating in class B output stages, they conduct for half the cycle of the input signal. So their conduction angle is 180 degrees. It should be mentioned, as we will see later on, that the conduction in the negative half cycle is provided by another transistor, which also operates in class B mode. And the currents from the two transistors, they are combined to generate the load current. As an intermediate class between class A and class B amplifiers, there is this class ADE amplifier, which is biased at a collector current which is greater than 0 but smaller than the peak value of the signal current. So a transistor conducting in class AD mode has a collector current waveform which looks something like this. So since it is biased at a current IC which is greater than 0 but smaller than the peak value of the current, the transistor will conduct for the complete half cycle, and then it will partially conduct for the other half cycle, because the transistor cannot conduct negative currents. So when the overall instantaneous value of the current becomes negative, the transistor goes into cutoff. So a transistor operating in class AB mode has a conduction angle which is greater than 180 degrees, but is smaller than 360 degrees. So its conduction angle is in between the conduction angles for class A and class B amplifiers. So its conduction angle is smaller than the conduction angle of a transistor in class A mode, but it is greater than the conduction angle of a transistor operating in class B mode. That is why these amplifier stages, they are called class AB amplifiers. So class AB amplifiers, they have another transistor which conducts during the negative half cycle, and just like this transistor conducts fully during the positive half cycle and partially conducts in the negative half cycle, the other transistor will partially conduct in the positive half cycle and will fully conduct in the negative half cycle. So its conduction angle again will be greater than 180 degrees, but smaller than 360 degrees. So the two transistors in class AB amplifier, they conduct for an interval that is greater than the half cycle of the input signal current. And again, the current from two transistors is combined in the load resistor to generate the load current. Finally, there is a class C amplifier or a class C output stage, which is biased such that it conducts for an interval which is less than half cycle of the input signal. And the resulting conducted current or the resulting collector current waveform for the transistor is shown in this diagram here. So you can see that it conducts for an interval which is smaller than the half cycle of the input signal. So from 0 to 2 pi, it does not conduct from pi to 2 pi, and in the first half cycle from 0 to pi, it only conducts between from this point onwards to this point in time. So it conducts for less than a half cycle of the input signal. So in this case, because this waveform is not sinusoidal, this is the output waveform of the class C output stage, and it's not sinusoidal, which means that it will contain harmonics. So we get rid of those harmonics by passing this waveform through an LC band pass filter, which is tuned to the frequency of the input signal. So that LC band pass filter will recover the sinusoidal signal from this waveform, whose frequency is equal to the frequency of the input signal, and it will reject all the other harmonics. So this waveform is passed through an LC bandpass filter, which generates the required sinusoidal signal at the output. So all of the amplifier configurations that we have studied so far, BJT amplifier configurations, that is the common emitter, common base, and common collector configurations, they're all biased at such a value of the current that they conduct during the whole cycle of the input signal. So all of those BJT-based amplifier configurations, they can be classified as class A amplifiers, because all of them have a conduction angle of 360 degrees. They are biased such that the instantaneous conducted current is always positive, and hence they conduct for the whole duration of the cycle of the input signal. However, common emitter and common base amplifiers, they have moderately large output resistance, which means that only common collector amplifier or common collector configuration, which has much lower output impedance, is best suited for use as an output stage. So we will not use common emitter and common base as class A amplifiers because they have moderately large output resistance. Only common collector configuration is typically used as a class A amplifier because of its much lower output resistance. So the figure here on the right shows a class A amplifier in which the transistor Q1 is configured as a common collector amplifier. That is, the input is applied at the base, and the output or the load is connected to the emitter. And this transistor Q1 is biased with the current capital I through this circuit made up of Q2, Q3, and R. And this circuit is called a simple current source. So the circuit made up of Q2, Q3, and R is used to bias this transistor Q1 with the current capital I. And this sub-circuit is called a simple current source, in which Q3 is actually a diode connected transistor. That is, it is a transistor whose collector and base terminals are shorted to each other. So the collector base junction is shorted out, and we are only left with the forward biased emitter base junction. So it behaves essentially like a diode, which is why I have labeled it as Q3, but I have represented it with a diode, which means that it is a diode connected transistor. It's not a physical diode. It's a transistor whose collector and base terminals have been shorted together, so it acts as a diode connected transistor. So before we can analyze this circuit, it is imperative that we go through the working of this sub-circuit, which is the simple current source. A simple current source is actually an implementation of a basic current mirror, which in turn is an implementation of an ideal current source. So the circuit of a BJT current mirror is shown in this diagram here, in which this ideal current source labeled IREF and this transistor QREF, they make up what is called as the reference circuit. So this is the reference branch of the current mirror, in which QREF is connected such that its collector and base are shorted to each other. So QREF behaves as a diode connected transistor, and it will always be in active mode because its VCB is 0. Remember, the collector base junction for a transistor to be operating in active mode must be reverse biased. So VCB equal to 0 means that it is essentially reverse biased. And the base to emitter voltage, because of this physical short circuit, is equal to then the collector to emitter voltage. So when the transistor is conducting, this base to emitter voltage is typically 0.5 to 0.7 volts, which is greater than the saturation voltage of the device. So this diode connected device will always be in active mode. So the fundamental requirement for the operation of a BJT current mirror is that the two transistors Q and QF, they must be matched. That is, they must have same parameters except the area of the emitter base junction, which may differ between Q and QREF. And so this is always in active mode, but this should be operated in active mode. So this should be constrained to operate in active mode, which means that V0 should not go below or equal to, should not be less than or equal to VCE sat. It should always be greater than VCE sat, V0. Otherwise, the current through Q will not be constant. So we know that the collector current of an NPN BJT in active mode, if we ignore for simplicity the early effect, is given by this relation. So the collector current IC is a function. In fact, it has an exponential dependence on VBE, and it remains constant irrespective of what VCE is, under the assumption that the early voltage is infinity. That is, we are ignoring the early voltage. So IS is the scale current and VT is the thermal voltage. So if I take the ratio of the collector current of Q, so if I represent the collector current of Q as IC and the collector current of QREF as ICREF, which is the current flowing through this branch, then since the base to emitter voltage for Q and QREF is the same, I can write IC like this, and I can write ICREF with a similar expression, in which the scale current will be different, VBE and VT and the exponential dependence will remain the same. So when I take the ratio of the two collector currents, this exponential dependence will get cancelled out, and I'll be left with the ratio of IS to ISREF. So IS is the scale current of Q, ISREF is the scale current of the reference transistor. So this ratio of collector currents is actually equal to the ratio of the scale currents. And since the two devices are matched, except in their emitter-based junction area, we know that the IS for Q and QREF will only differ in the area of the emitter-based junction. So since the scale current is proportional to the area of the emitter-based junction, this ratio for matched transistors will be equal to the ratio of the area of the emitter-based junction of Q to the area of the emitter-based junction of QREF. Because all the other parameters are same, they will get cancelled out. So this ratio is equal to the emitter-based junction areas of Q and QREF. And this ratio is typically represented by M. So we define M as the ratio of the collector current of Q to the collector current of QF under the assumption that Q and QF are matched. If they are fully matched, that is, if their emitter-based junction areas are also the same, then M will be 1, which means that IC will be equal to ICF. However, they may be different, the emitter-based junction areas of the two devices, and then M may assume values other than 1. So if I denote the base current of QREF with IDREF, we can see that IREF divides into the collector current of QREF and in this branch. And this branch contains the base current of QREF and the base current of Q. So if I represent the base current, so the base current of Q is equal to the collector current of Q divided by beta. So I can write IREF as the sum of ICREF plus IBREF plus IB, where IB is the base current of Q. ICREF is equal to IC over M because I have just defined IC over ICREF to be equal to M. And IBREF is equal to IC over beta. ICREF over beta, which again ICREF is IC over M, so it is IC over beta over M. And IB is just IC over beta. So simplifying this, we get IC over IREF. So previously we found IC over ICREF. Now we obtain IC over IREF. That is the ratio of the collector current of Q to this reference current, which is given by this factor. That is M over 1 plus M plus 1 over beta. And since the collector current of Q is equal to I naught, so IC over IREF is equal to I naught over IREF. So this ratio here is called the current transfer ratio of the basic BJT current mirror. So given IREF, I can bias the load, which I have shown here with this dotted line here. So this dotted line represents some load, maybe transistor or class A amplifier. So given IREF, I can, by adjusting M, generate a desired current I naught through this load. So this is what basic current mirror does. It generates a constant current for biasing of different loads. So if we can further simplify this expression under the assumption that beta is infinity. Although beta is not infinity, but if we ignore the effects of finite beta, which is equivalent to saying that if we assume alpha to be 1, which is not a very bad assumption. So if I ignore beta, assuming alpha to be 1 means that beta is infinity. So if I take beta to be infinity, then this ratio of I naught over IF simply becomes equal to M. That is, the current copied into this branch containing Q is actually equal to IREF. So this is the copied current from this reference branch. So if we ignore the effects of beta, then the copied current is actually M times IREF. So if M is 1, then we get an exact replica of IREF in this branch. So what basic current mirror does is that it mirrors the current from the reference branch towards the load branch. If we ignore the effects of beta and if we assume that M is 1, that is the two devices are perfectly matched, then the current IREF is mirrored as I naught into this branch, hence the name current mirror. Which is why M is also called the nominal current transfer ratio. So the nominal current transfer ratio is obtained when Q and QREF are perfectly matched and beta is very large, in which case we will obtain I naught as IREF. That is, the current IREF will be mirrored onto this branch I naught. So we can implement this current source through a resistor here, which is labeled as RF. So please note that this is not a very good implementation. There are other more sophisticated implementations. This is a very crude modeling of the ideal current source, but it is simple to analyze, which is why we will proceed with this model. So this RF here actually models the ideal current source. So if we replace the ideal current source with RF, we obtain what is called as the simple current source circuit. So this is the circuit that we have used to bias the class A amplifier. So you can see that this part is actually this part, and the dotted line here is it represents this load here, which is Q1 connected in a common collector configuration. So this bit of the circuit, this portion of the circuit actually acts as the load to the current source, which is made up of this portion of the circuit, in which Q3 is this diode connected transistor. So the reference current we can find, because I is set up by this current source, so I is actually equal to I naught, and I naught is given by I ref. It is given in terms of the current in the reference branch. So we need to find the current in the reference branch when we have implemented the ideal current source with this resistor RF. So we can find that current very easily. So assuming that the current flows, and it does flow in this direction because QRF cannot conduct in the opposite direction. So the current flows downwards through RF, and it is given by the voltage drop across RF divided by RF. So voltage drop across RF is the difference of voltage at this node and this node. So this node is 0, this node is grounded, so the voltage at this node is 0. The voltage at this node is the same as the voltage at this node. So the voltage at this node is actually equal to VBE plus the voltage at this node, which is minus VCC. So 0 minus VBE minus VCC is the voltage drop across RF, which is equal to VCC minus VBE over RF. So VCC minus VBE is actually the voltage drop across RF, and VCC minus VBE divided by RF is the reference current, IREF. So once we know the reference current, we can find, using this equation, the copied current, which in the context of this circuit is equal to I. So knowing the reference current, we can find what is I. So this value or given I, we can find the required value of R. Which generates the reference current, which in turn gives us the required I. So using these equations, we can bias this common collector amplifier with the current source, with the current I, which should be greater than the peak value of the collector current due to the signal, so that Q1 conducts during the whole cycle of the input signal Vi. So when Vi is 0, so V subscript small I corresponds or represents the AC component of the total input signal Vi. So when Vi is 0, that is under DC setting, the load voltage is given by the voltage at this node with respect to ground. So the voltage at this node is the voltage across the transistor Q2, that is VCE2, plus the voltage at the emitter, which is minus VCC. So when there is no signal applied at the base of Q1, then the voltage at the load is given by this expression, which is the DC value of VCE across Q2 minus VCC. And since there is no signal in the circuit, the output voltage only has DC component, no AC component. And by design, this DC component is typically set to 0, which then means that under DC conditions, that is when there is no signal applied to the base of Q1, under DC conditions, when the DC voltage is 0, there is no current flowing through RL. When there is no current flowing through RL, then this bias current is actually equal to the emitter current of Q1, because emitter current of Q1 is I plus IL, but there is no current flowing through RL under DC condition. So IE1 is just equal to I. So the DC current flowing through the emitter of Q1 is equal to the biasing current, which gives us the collector current, the DC collector current of Q1 equal to this expression, which can be approximated to be equal to I, because beta over beta plus 1, if beta is large, is almost 1. This is alpha, so it's almost 1. So the collector current of Q1 under DC conditions is approximately equal to I. So please note that this design requirement that the DC load voltage be 0, it in turn imposes a constraint on the DC value at the input of the amplifier. That is the DC value here, because the voltage here is equal to, or should I say, the voltage here, the load voltage is equal to VI minus VBE. So if the DC voltage here is 0, then the DC voltage here should be equal to VBE1. Only then VL will be 0. So under the quiescent conditions, under the DC conditions, so which is also called the quiescent state of the amplifier. So quiescent state corresponds to the state of the amplifier when there is no signal applied to the amplifier. So under the quiescent conditions, when the DC load voltage is constrained to be 0, there is a constraint on the DC component of the voltage at the base, that it should be equal to the VBE1, the forward bias voltage across the base emitter junction of Q1. Also note that the zero biasing at the load is only possible because of the dual supply operation. Because previously we biased the amplifiers using single supply, and then there we could not set the output DC to 0 because the transistor does not conduct in the opposite direction. But here, when the output DC voltage is 0, then the transistor can still conduct in the negative direction because of this negative VCC. So the voltage at the collector of Q2 can swing in the negative direction as long as it is greater than minus VCC. As soon as it approaches minus VCC, this transistor Q2 will go into saturation. So because of the fact that we are using dual supply to bias this amplifier stage, we can actually satisfy this design criteria of 0 load voltage under quiescent conditions. Otherwise, in case of a single supply operation, there has to be a DC voltage at the output, and then the output must be capacitively coupled with the load to kill that DC voltage across RL. So like mentioned before, since the output stages are the final stages of multi-stage amplifiers, they contain large currents and voltages, so the small signal approximation may not be applicable. But under the assumption that the voltages and currents are small enough so that we can use the small signal approximation, we wish to find out the small signal voltage gain of class A amplifier. So, and this small signal voltage gain can be easily found by observing, and in fact by realizing that Q1 is configured. Since Q1 is configured in common collector configuration, and we have already analyzed common collector configuration in great detail, so we can use the expressions obtained for small signal voltage gain of common collector amplifier to find the small signal voltage gain of this circuit. So by observing that the AC resistance in the emitter branch of Q1 is actually small r naught of Q2, that is the resistance seen between this node, which is the collector of Q2 or the emitter of Q1. So the resistance seen between this node and ground looking into this node is small r naught 2. I encourage you to draw the small signal AC equivalent circuit of this portion by short circuiting the VCC to ground, and see for yourself and verify that the resistance seen between this node and ground looking into this node is small r naught of Q2, which I have represented as small r naught 2. So this small r naught 2 represents the resistance in the emitter branch, the AC resistance in the emitter branch of Q1. So I replaced this, or I considered this small r naught Q of Q2 as the AC emitter resistance of Q1. So by simply replacing RE in the expression obtained for the small signal voltage gain of common collector amplifier with the small r naught 2, we can obtain the voltage gain in going from this node to this node directly through this expression. So this is the same expression derived before. The only difference is that I've replaced RE with small r naught, capital RE with small r naught 2. And under this very reasonable assumption that the small RE1, which is the small RE of Q1, that is, it is the resistance between base and emitter looking into the emitter of Q1. Since this is very small, it is much smaller than this parallel combination. Under this assumption, very reasonable assumption, we can approximate the gain of the circuit to be equal to 1. So, and this is expected because the gain of small signal voltage gain of common collector amplifier is very close to 1, is indeed very close to unity. So the small signal voltage gain of class A amplifier, because class A amplifier is made out of common collector amplifier, the small signal voltage gain of class A amplifier is almost unity. So here V subscript small l is actually the AC component of this V subscript capital L. So please notice that this convention of the lowercase letter and uppercase subscript represents the total quantity. Similarly, this represents the total current. But under quiescent conditions, that is when there is no signal, under DC conditions, the DC load voltage and the DC load current, they are constrained to be 0. So the total load voltage and total load current, they are actually AC in nature because they don't have any DC component. But I will keep on representing them with this notation in order to maintain consistency. So I will keep on representing the load voltage, although it is AC in nature, I will represent it with capital subscript, and I will represent this load current with capital L in the subscript, although the DC content of this load current is 0. So from the circuit of class A amplifier, we see that VL is equal to VI minus VBE1, and IE1 is I plus IL. You can easily see that VI minus VL is VBE1, so VL is VI minus VBE1, and IE1 is the sum of I and IL. So if we ignore the dependence of VBE on IE, that is VBE changes by about 60 millivolts for every factor of 10 change in IE. So this is a rather weak dependence. So if we ignore this dependence, then we can see that the load voltage is just a shifted version of the input voltage, which is, so the load voltage is shifted by VB. So the input voltage is shifted by VBE at the load. So the load voltage is a shifted version of VI. So as VL increases in the positive direction, VCE1 decreases because the load is connected at the emitter of Q1. So as VL, which is equal to VE1, increases, VCE1, which is VCC minus VE1, because the collector of Q1 is connected to VCC. So collector to emitter voltage of Q1 is VCC minus VE1. So as VE1 increases in the positive direction, VCE1 will decrease and Q1 will be driven towards saturation. And the maximum of the load voltage, the maximum load voltage or the maximum value that the load voltage will obtain will occur when Q1 enters saturation. So under this condition, I replace VL, I choose to denote VL with VL maximum positive. So the maximum value of the load voltage, it occurs when Q1 enters saturation. That is VCE1 equals VCE1 sat. So VCE1 is in turn equal to VCC minus VL, which under this condition has been represented as VL maximum positive. So VL maximum positive is found to be VCC minus VCE1 sat, which is approximately equal to VCC because VCE sat is a small value, about 0.2 to 0.4 volts. So this maximum is almost equal to VCC, but strictly speaking, it is less than VCC by an amount VCE sat. On the other hand, when VL increases in the negative direction, then IL increases in the negative direction. That is when VL is swinging in the negative direction, IL flows in the negative direction. So IL, when VL swings in the negative direction, IL flows up RL. So IL will flow in the opposite direction. It will flow upwards through RL. So IE1 plus IL will equal capital I. So since capital I is assumed to be constant, increasing IL in the upward direction will mean that IE1 will decrease. So as VL swings in the negative direction, IL will increase in the upward direction. And because this current is almost constant, IE1 will decrease. So as VL swings in the negative direction, Q1 is driven towards cutoff mode. Moreover, because the load voltage is equal to the collector voltage of Q2, as VL swings in the negative direction, VCE2, which is equal to the voltage at the collector of Q2 minus the voltage at the emitter of Q2. Voltage at the emitter of Q2 is minus VCC. So VCE2 is VC2 plus VCC. So as VC2 swings in the negative direction, this sum will decrease, which means that Q2 will be driven towards saturation. So as VL swings in the negative direction, Q1 is driven towards cutoff mode and Q2 is driven towards saturation mode. So it's a race between Q1 and Q2. If Q1 enters cutoff mode before Q2 enters saturation mode, then the maximum negative value of the load voltage will be limited by Q1. If Q2 enters saturation mode before Q1 can enter cutoff mode, then this maximum negative value of the load voltage will be defined by Q2. So when Q1 enters cutoff mode, IE1 will become 0 and minus IL will become I. In other words, I will become minus I. In other words, IL will become minus I. So minus IL will become I, or minus I will become IL. This means that VL at that point will be minus capital I times RL. So this condition here, this maximum is obtained when Q1 enters cutoff mode. On the other hand, when Q2 enters saturation mode, then the load voltage, VC2 is the load voltage here, it will become equal to VCE sat 2 minus VCC. So this load voltage, which is represented as VL maximum negative under this condition, will become VCE2 sat minus VCC. So this is the voltage obtained when Q2 enters saturation mode. So if this happens before this, then the maximum will be given by this value. On the other hand, if this happens before this, then the maximum will be given by this value. So it depends upon this condition. If the magnitude of this is smaller than the magnitude of this value, then this will occur earlier. This will happen earlier than this. On the other hand, if it is the other way around, then this will happen earlier than this. So, like I said, VCE sat is pretty small, 0.2 to 0.3 volts. Minus VCC plus VCE2 sat is almost equal to minus VCC. And this is the maximum negative that VL can get. VL cannot go below minus VCC. This is the maximum negative that VL can get. So in order to maximize swing, we enforce this condition so that VL maximum negative is given by this number, which is the most negative VL can get. So enforcing this condition gives us a condition or a constraint on the biasing current, that it should be at least equal to this value, greater than equal to this value, or at least equal to this value. So these equations can be, using these equations, we can generate this graph between VL and VI. So this is actually a graphical representation of what I've just explained. So VL is VI minus VBE. So within this portion of the curve, when neither Q1 nor Q2 limits the magnitude of VL, then this straight line is actually the plot of this equation. So the slope of this equation is 1. That is why it's a straight line passing through VBE1 with unity slope. So VL is just a shifted version of VI. So as VI, as VL increases, it can go up to a maximum of VCC minus VCE sat, because beyond this value, Q1 will enter saturation mode. So VL cannot go beyond this value. It will get saturated at this value. On the other hand, when VL swings in the negative direction, it can either get saturated at minus IRL, which will mean that at this point Q1 has entered cutoff mode, or it can get saturated at this value, which means that Q2 has moved into saturation mode. So whichever of the two is smaller in magnitude will define the swing of the output load voltage in the negative direction. So under this constraint, IRL in magnitude is either made equal to or greater than the magnitude of this number. So minus IRL is either made equal to this number or smaller than this number. And in that case, the maximum swing will be determined by this quantity, which also makes the swing in both directions symmetric. So VL is limited in the positive swing by this number and in the negative swing by the negative of this number. So by forcing this constraint, we not only get maximum swing on the negative side, but we also get symmetric swing on the positive and negative sides. So this curve, which is the plot of the load voltage against the input voltage, is called the voltage transfer characteristics of the class A amplifier. So if we ignore VCE sat, because it's, like I said, it's quite small, especially in the context of large magnitude of the signals under consideration, because the output stage typically deals with large magnitude signals. So in this context, VCE sat is even more insignificant. So if we ignore VCE sat, then from equations 9 and 10, we can see that VL swings from VCC to minus VCC if I is set equal to this value. So from 9, we see that ignoring this quantity, VL maximum positive is equal to VCC, and ignoring this quantity, VL maximum negative is equal to minus VCC if I, capital I, is at least equal to this value. So we set capital I equal to, so ignoring VCE2 sat, we set capital I equal to the magnitude of minus VCC divided by RL, which is equal to VCC over RL. So when I is equal to VCC over RL, VL maximum negative swings, the maximum value of the load voltage in the negative direction is equal to minus VCC. So VL swings from VCC to minus VCC. So assuming that the class A amplifier is also linear, if the input signal is a sine wave, then the output signal will also be a sine wave. So the load voltage, which is under the assumption that input is a sinusoidal signal, the load voltage will be a sinusoidal signal, which will swing from VCC to minus VCC if the bias current is set equal to this value, ignoring VCE sat, which gives the collector current for Q1 denoted by IC1. This is the total collector current in terms of the total emitter current. So we can ignore alpha 1 and approximate the total collector current by the sum of the biasing current and the load current. So the load current, so bias current is equal to VCC over RL, and load current is given by VL over RL. So both total load current and total load voltage, they are AC in nature. Their DC content is 0. So when VL swings from plus VCC to minus VCC with a sinusoidal dependence, then VL is VCC sin omega t. So VL over RL, which is IL, will be equal to VCC over RL times sin omega t. So this is an AC signal with 0 DC value. This is a DC value, however. So total collector current will have a DC current. So the instantaneous power dissipation in Q1, that is instantaneous power dissipated by Q1, which we denote with PD1, is given by the product of the voltage across Q1, which is VCE1, times the collector current of Q1, which is IC1. So VCE1, on the other hand, is given by VCC minus VL. So VL is VCC times sine omega t, and VCE1 will be VCC minus VCC times sine omega t. So you invert this waveform and add VCC, you'll get the waveform from VCE1. So plotting these equations, we see that, so like I said, I've assumed the input signal to be sinusoidal and class A amplifier to be linear. So the output is sinusoidal, swinging from VCC to minus VCC. VCE1 is given by flipping this value, flipping this waveform. So minus VL plus VCC. So I have flipped this and then I add VCC to it. So the DC value of VCE1 is VCC, and it's given, it has an inverted waveform relative to VL. IC1 is given by a sinusoidal waveform. So this is I. So IC1 is I plus I sine omega t. So it's this waveform. So its DC value is I, and it swings from I to 2I down to 0. Because it's I plus I sine omega t. So at the peak, it will have value 2I, and at the positive peak. And at the negative peak, it will have value of 0. So the DC value of the collector current is I. So if I multiply these two waveforms, I'll get the instantaneous power dissipation, which is shown here in this diagram. So the maximum of the power dissipation in Q1 is given by VCC times I. So the supply voltage times the bias current. And this maximum occurs when the collector current has a DC value of I. VCE1 is equal to VCC. So the collector current is equal to I. VCE1 is equal to VCC, and VL is equal to 0. So at T is equal to 0, when VL is 0, VCE1 is VCC, and IC1 is I. Power dissipation is maximum, equal to VCC times I. So from these waveforms, we can conclude that the maximum power is dissipated in Q1 under quiescent conditions. That is when VL is 0. VL is 0 only when there is no signal applied to the amplifier, because the DC content of the voltage, load voltage, is 0. So under quiescent conditions, when there is no VI, VL is 0, and the power dissipated in transistor Q1 is the maximum, equal to VCC times I. So Q1 dissipates maximum power under quiescent conditions. This is also called quiescent power dissipation, and hence it must be able to withstand this power dissipation of VCC times I. Because this condition, this quiescent condition, when there is no input signal applied at the base of Q1, because this condition can prolong for long intervals, this quiescent condition can persist for longer time intervals. So transistor Q1 must be able to withstand this power of VCC times I, because if there is no signal applied to the class A amplifier for longer periods of time, then the power dissipated in Q1 will be a constant VCC times I. So Q1 must be able to withstand this power dissipation of VCC times I units. As we just saw, the power dissipated in Q1, it depends on the value of the current through Q1. That is, it depends on IC1, which in turn depends on the value of the current through RL, which means that it depends on RL, because the current through RL, given the load voltage, depends on RL. So if there is no RL, if the output is open circuited, then in this case there is no IL. IC1 is equal to I, which is a constant, and the instantaneous power dissipation PD1, because now the collector current becomes constant. Instantaneous power dissipation, which is the product of IC1 and VCE1, will be given by VCE1. So if we simply multiply VCE1 by capital I, because I is a constant, so the power dissipation will have a waveform like this, with an average value of VCCI and a maximum peak value of 2 times VCCI. So we observe that the maximum power dissipation, the maximum power is dissipated when VL is at its when VC1 is at its positive peak. At this point, VL is at minus VCC. So multiplying this with I will give us a maximum power dissipation of 2 VCCI at this positive peak, at which load voltage is equal to minus VCC. So the maximum power dissipation is observed in Q1 equal to 2 VCCI when VL is equal to minus VCC and VCE1 is equal to 2 times VCC. It is at its maximum positive peak of 2 times VCC. And the average value, like I said, is equal to VCC times I. On the other hand, if the output is short-circuited, that is, if RL is 0, then for a small, even for small positive, even for small magnitude load voltages, an infinitely large load current will flow through the resistance, through the short-circuited resistance, which will cause a very, very large collector current through Q1. And if this, which will in turn dissipate large amounts of power in Q1. So if this condition persists, then this large power dissipation can will eventually burn the transistor. This is why almost all of the output stages, they are typically equipped with short circuit protection circuits, which sense whenever the output is shorted to ground, they protect the transistors in the class ADE and in the output stages from getting burned up. The power conversion efficiency is another very important design requirement for the class A amplifiers in general for output stages. Like I mentioned before, the power dissipation within the output stage should be as small as possible, and maximum power must be delivered to the load. So this efficiency of an output stage can be gauged by defining power conversion efficiency as the ratio of the average power delivered to the load to the average power supplied to the circuit by the source. So PL is the average power delivered by the circuit to the load, and PF is the average power consumed by the circuit, extracted by the circuit from the DC voltage sources. So assuming that the signals flowing through the amplifier are sinusoidal and the output stage is linear, load voltage will be sinusoidal, and the average load power will be given by VL square over RL, where these symbols they represent an operator which computes the average value of its argument. So since RL is constant, VL is varying, so we need to compute the average value of VL square. And since VL is sinusoidal, so it will be positive from 0 to pi as well as from 0 to 2 pi. So if we compute the average value of VL square, you can find it to be equal to VL peak square by 2, where VL comma peak is the peak value or the amplitude of VL. So the peak value square divided by 2 is the average value of VL square, and the average power delivered to the load is given by the peak value of the load square divided by 2RL. So since the class A amplifier was biased using 2 power supplies, plus VCC and minus VCC, it draws power from both of the DC sources. So the transistor Q1 is biased at the current capital I. Q2 contains the bifacial current capital I, which is equal to, under the quiescent conditions, equal to the emitter current of Q1, which is approximately equal to the collector current of Q1 if we take alpha to be 1. So transistor Q1 is biased at approximately this current I, and so the average power, this is the average current. So if we look at the curves, go back and look at the curves, then the collector current has an average current of I units. So the average current, the average collector current through Q1 is I, capital I. So this means that the average current drawn from the DC source, VCC, is equal to I, and multiplied by the voltage of the DC source, which is VCC. So VCC times I gives us the average power supplied by the DC source plus VCC. So since the voltage of the source is VCC and the average current drawn by Q1 from VCC is I, so the average power applied by the source plus VCC is equal to VCC times I. Similarly, since the average current through Q2 is a constant equal to I, the average power drawn by Q2 from the DC source minus VCC is equal to, again, VCC times I. Because the current, average current pushed into the supply minus VCC by the transistor Q2 is I, then minus I is the current which is supplied by the source minus VCC. So minus VCC times minus I gives us the power supplied by the source minus VCC, which is equal to VCC times I. So we can, using these expressions, the total power supplied by the sources to the circuit is equal to 2 times VCC times I. So using this definition and this expression for the average load power, we can find the efficiency which is given by this expression. So since we have assumed that VL swings between plus VCC and minus VCC, and we have assumed that IRL is greater than the magnitude of minus IRL, which is IRL, is greater than the magnitude of minus VCC, which is VCC. So the peak value is always less than equal to VCC, and it is always less than equal to IRL. And a maximum power conversion efficiency is observed when VL peak is equal to IRL and VL peak is equal to VCC. In other words, when IRL is equal to VCC, which was the case when we plotted the signal waveforms in figure 12, there we set I to be equal to VCC over RL by setting VCC equal to IRL and ignoring VCE back. So under this setting, we obtain a maximum power conversion efficiency of 25% for class A amplifiers. So we observe that class A amplifiers have a low power conversion efficiency. And in practice, the peak value of the load voltage is kept smaller than VCC by more than VCE stack, because as a VL peak or as the instantaneous value of the load voltage approaches VCC, then because of the non-linearity of the voltage transfer characteristics of the BJT, the amplifier no more remains a linear circuit. So close to saturation, the non-linear effects of the circuit, they tend to distort the output. So VL peak is kept smaller than VCC by more than VCE stack to avoid such non-linearities and distortion of the output when Q1 is driven close towards saturation. So this results in an even smaller efficiency of about 10 to 20% for the class A amplifiers. So class A output stages, they are low power conversion efficiency amplifiers, which is why they are not used in high power applications. The other type of output stage, which has a much larger power conversion efficiency compared to the Class A amplifier, which I'll show later on, is the Class B output stage, which is biased at zero current. So Class B output stage consists of complementary devices as shown in this diagram here. So this is a Class B amplifier circuit, which uses an NPN as well as a PNP transistor. So it uses both transistors. So it makes use of complementary output devices. And both of these two are connected in a common collector configuration. That is, the input is applied to the base of the two transistors, and the output is taken from the emitter of the two transistors. So if QN receives input at the base and output is taken from the emitter of QN, and QP as well is excited at the base, and the output is taken from its emitter. So both of these transistors are connected in a common collector configuration. The two transistors, QN and QP, they can be seen. It can be seen that they cannot conduct simultaneously because VBE for QN is equal to minus VEB for QP. So base to emitter voltage of QN is equal to the base to emitter voltage of QP. So if base to emitter voltage of QN is positive, so if QN is forward biased, then base to emitter voltage is positive, which means that the base to emitter voltage of QP is positive, which reverse biases the emitter base junction of QP. So on the other hand, when emitter to base voltage of QP is positive, that is when the base emitter junction of QP is forward biased, then emitter to base voltage of QN is also positive, which means that the base emitter junction of QN is reverse biased. So when QN is conducting, QP is in cutoff, and when QP is conducting, QN is in cutoff mode. So it must also be kept in mind that in order to forward bias the base emitter junction, let's say for QN, the base emitter voltage of QN should be at least equal to 0.5 units. Similarly, to forward bias the base emitter junction, emitter base junction of QP, the emitter base voltage must be at least 0.5 volts or so. So QN and QP, they will not conduct until their respective base emitter junctions are forward biased by voltages of around 0.5 to 0.8 volts. And just like the Class A amplifier, the DC component of the load voltage for Class B amplifier is constrained to be zero as well. So under quiescent condition, that is when there is no signal applied, the DC voltage across the load as well as the DC current through the load, they are constrained to be zero. So initially, when there is no signal at the base, there is no voltage at the base. When Vi is zero, the two complementary devices are in cutoff mode. And since there is no load current, there is no load voltage. And as soon as Vi starts increasing in the positive direction, QP remains in the cutoff mode because VEBP is equal to Vi. So you can see that when Vi is zero, VL is zero. So this node is virtually at ground. So as soon as we increase Vi, as soon as Vi becomes positive, then voltage at this node with respect to ground is positive, which means that voltage at this node with respect to this node is positive, because just at the moment when Vi starts increasing, this node is at ground. So the voltage at this node with respect to this node, which is Vi, is equal to minus VEB, or is equal to VBEP. So Vi is equal to VBEP, and since Vi is increasing and is positive, VBEP is positive, which keeps the emitter base junction of QP reverse bias. So as soon as Vi starts increasing, QP remains in cutoff mode. However, since the base and emitter terminals of the two devices are connected, so as soon as Vi starts increasing, Vi with respect to this node, because as soon as it happens, this node is at ground because VL is 0. So Vi is also equal to VBEN. So unless this device starts conducting, this voltage will be at ground. So Vi will be equal to VBEN as well. So Vi, since it is increasing, it is equal to VBE of Qn. So when Vi exceeds about 0.5 volts or so, then VBE of N exceeds 0.5 volts, and the emitter base junction or the base emitter junction of Qn becomes forward biased, which turns the transistor Qn on and conducts a current. Because QP is in cutoff mode, so the current conducted by transistor Qn will flow through the load RL. So the current conducted through Qn is equal to IL. So as soon as Vi exceeds about 0.5 volts or so, Qn conducts a current IL through the load resistor RL, and this gives us this equation for the load voltage. That is Vi minus VL is equal to VBE of N. So this gives VL as Vi minus VBE of N. And in the following analysis, again, we will assume we will in fact ignore the dependence of VBE on IE, which was discussed before, that VBE changes by about 60 millivolts, or a factor of 10 change in IE. So ignoring that dependence, we see that the load voltage is given by is given as the shifted version of the input signal. So VL is Vi minus some constant, VBE of N. Ignoring the small changes in the base emitter voltage of Qn. So on the other hand, when Vi is 0, there is no current flowing through. The circuit. VL is 0, and as soon as Vi becomes negative, so at the point at which it starts to increase in the negative direction, this node is still at, because the transistors are not conducting, this node is still at 0 voltage. So Vi is not only equal to VBE, it is also equal to VBE of P. So when Vi becomes negative, or as it starts to increase in the negative direction, VBE starts to increase in the negative direction, which keeps Qn in the cutoff mode, because the emitter is, or the base emitter junction of Qn is reverse biased. But since Vi is equal to VBE, VEB is equal to minus Vi. So as Vi is increasing in the negative direction, VEB is increasing in the positive direction. So when Vi drops below minus 0.5 volts, VEP increases beyond 0.5 volts, turning QP on. So the emitter base junction of QP will become forward biased and QP will turn on. So since VBE of N is equal to Vi and Vi is increasing in the negative direction, Qn remains reverse biased. Qn remains in cutoff mode. Base emitter junction of Qn remains reverse biased. And when Vi goes below this minus 0.5 volts, QP turns on because its emitter base voltage goes beyond 0.5 volts. And it starts to conduct the current IL through the load resistance RL in the opposite direction. So now QP will conduct the current IL in the opposite direction. So Qn conducted the current through RL in this direction, down RL. QP will conduct current in the opposite direction. So IL will flow up RL and through QP. So IL will flow in the opposite direction, which will result in this equation for the load voltage. So this can directly be seen from this circuit, that VL minus VI is equal to VEB of QP. So VL is equal to VI plus VEB of QP. Again, ignoring the dependence of the VEB on IE, we see that VL is a shifted version of VI. So VL is VI plus some shift. So VL is given as a shift in the input signal VI. So in short, we see that QN conducts when VI is greater than about 0.5 volts, and QP conducts when VI is less than about minus 0.5 volts or so. So this amplifier configuration is called the push-pull configuration, because as we have seen, when QN is conducting, it pushes the load current through RL in the downward direction through RL. But when QP is conducting, it pulls the load current in the opposite direction, up RL, up the load resistor RL through QP. So QN pushes the current through RL, and QP pulls the current through RL. So that is why this amplifier configuration is also called the push-pull configuration. The maximum load voltage is observed when Q1 enters saturation, just like the class A amplifier. As the load voltage increases, the VCE of Qn will decrease, and the maximum of the load voltage will be observed when Q1 enters saturation mode. Similarly, as the load voltage increases in the negative direction, VCE of QP will decrease, and the maximum negative of the load voltage will be observed when QP enters saturation, the saturation mode of operation. So the maximum load swing is given by these two bounding load voltages. So the positive swing is limited by VCC minus VCE sat of Qn, and the negative swing is limited by negative of VCC minus VEC sat of QP. So this diagram here shows the voltage transfer characteristics of the push-pull amplifier. So when VI is in between these two values, that is, when VI is less than 0.5 volts and is greater than minus 0.5 volts, none of the transistors, neither QN nor QP, conduct, and we get a zero voltage across the load RL, because there is no current through the load. And as soon as VI exceeds 0.5 volts, QN starts to conduct and it pushes the current through RL, and the expression between the load voltage and the input current is given by this equation. So this equation has a slope of unity. So when QP conducts, the equation is the expression between VL and VI is given by this equation, which again has a slope of unity. So when VI is greater than 0.5 volts, we get a straight line with slope of unity, and when VI is less than minus 0.5 volts, QP conducts, and we again get a straight line with a slope of unity. And VL rises to a maximum value given by VCC minus VCE N sat. At this point, Qn enters saturation mode, and maximum negative value of VL is given by minus VCC minus VEC P sat, at which point QP enters the saturation mode. So this region on the VTC, during which there is no conduction through the class B amplifier, is called the dead band on the VTC. And if we assume that the input voltage is a sinusoidal signal, then the output voltage is not exactly a sinusoidal signal. Due to this dead band, there will be regions on the curve during which the voltage will be zero. So during this time, So this is the amplitude. The y-axis is the amplitude and this here, this vertical line here is the time axis. So during this time interval, when the input voltage is less than VBEN, which is 0.5 volts, there is no conduction. So we get zero voltage. And as soon as VI becomes greater than this value of 0.5 volts or so, VL becomes equal to VI minus VBE of N. So we get a linear relation. So we get a linear, so since this relation is linear, so beyond this time, the output curve matches the shape of the input curve because we get a linear relation. But the magnitude of the maximum peak value here, the peak value of the output will be smaller than the peak value of the input by this amount, VBE, because VL is VI minus VBE. Similarly, when VI drops below 0.5 volts and is greater than minus 0.5 volts, during this time, there is no conduction either through Qn or Qp, and the voltage again is zero. And as soon as Vi drops below minus 0.5 volts, Qp starts to conduct. And we get a linear relationship between VL and Vi. So the shape of the output waveform is the same as the shape of the input waveform within this region, when as long as Vi is greater than smaller than minus 0.5 volts. So, but again, as was the case for the positive peak, the negative peak is smaller for the output voltage. The negative peak is smaller than the negative peak of the input voltage by about 0.5 volts or so, because VL is equal to Vi plus VEB. So VL is Vi plus VEB. So when Vi is at its negative peak, there will be some voltage added to the negative peak of Vi to get VL. So VL is smaller in magnitude at the negative peak than Vi. So we get an output waveform which resembles the input waveform, but is smaller in peak and has regions of zero conduction. So this is obviously not a sine wave because of these regions of zero conduction due to the dead band. So this distortion in the output signal is called the crossover distortion. So this crossover distortion introduced by this dead band in the voltage transfer characteristics of the class B amplifier makes the output a distorted sine wave. So it's not a pure sine wave, it's a distorted sine wave due to this crossover distortion, which obviously is undesirable, but unavoidable in the case of class B amplifier. So the power conversion efficiency of class B amplifier can be obtained by finding the average power delivered to the load divided by the average power drawn from the source, the two sources, VCC and minus VCC. So ignoring the crossover distortion and assuming that the output is a sinusoidal signal without any crossover distortion, then we can find the average power delivered to the load by the expression given in 17, which is for a sinusoidal load signal, load voltage, the average power is given by VL square over RL, and it is given by the average of VL square divided by RL, and the average of VL square is VL peak square divided by 2. So the expression in 17, which is VL peak square divided by 2RL, is the average power delivered to the load. And the average power drawn from the source depends on the half cycle of the input. So during the positive half cycle of the input, Qn conducts and it pushes current IL into the load RL. So IL is equal to the emitter current of Q1, and if we assume alpha for Qn to be approximately 1, then that emitter current is equal to the collector current of Qn. And collector current of Qn is actually the current which is drawn from the power supply plus VCC. So Qn is directly, the collector of Qn is directly connected to plus VCC. So the current drawn from plus VCC is the collector current of Qn, which is approximately equal to the emitter current of Qn, which is the load current. So this is the approximation under the assumption that alpha is 1. So this current has a maximum peak value, which is given by the peak value of the load voltage, VL peak. So VL peak divided by RL gives us the peak value of the load current. On the other hand, during the negative half cycle, Qn does not conduct, but Qp conducts, and it pulls the current minus IL from the load, and it pushes the current into the power supply minus VCC. So IS negative is the current flowing from the emitter of QP down QP into minus VCC, which is connected to the collector of QP. So again, assuming that alpha of QP is almost 1, we can, since minus IL is the emitter current of QP, if we assume that alpha is almost 1 for QP, then the emitter current of QP is almost equal to the collector current of QP, and the collector current of QP is actually IS negative, which is pushed into the power supply minus VCC. So again, this minus IL, this IL has a negative maximum peak value in the negative direction, which is again given by the negative peak of the load voltage divided by RL. So here in this diagram, I plot the currents IS positive and IS negative. So I'm assuming that the input swings in the positive direction from 0 to pi and in the negative direction from 0 to 2 pi. So during the positive half cycle of the input, IS plus is drawn by Qn and is sinusoidal because the input signal is sinusoidal. And assuming linear relationship, the output current and the output voltage will be sinusoidal, assuming linearity of the circuit. The output voltage and output current will be sinusoidal. So we get a sinusoidal half cycle of the current IS plus drawn by Qn with maximum peak value of VL peak divided by RL. On the other hand, during the negative half cycle, a similar half wave sinusoid current is pulled out of RL and pushed into minus VCC. So we get again a half sinusoidal waveform like this. But instead of drawing it in the negative direction, I have drawn it in the positive direction because IS negative. So if I go back to the circuit, so IS negative flows in this direction. So IS negative is the current drawn from VCC as the collector current of Qn. So it flows in this direction. Whereas minus IL, which is the emitter current of QP, which is approximately equal to the collector current of QP, which I have represented as IS minus negative, it again flows in this direction. So IS plus flows in the direction from top to bottom, and IS negative flows in the direction from top to bottom. So they are both in the same direction. So if I've drawn IS positive as swinging in the positive direction, then I must draw IS negative as swinging in the positive direction as well, because in the context of the circuit, they are both flowing from top to bottom, having the same direction. It's just that through the load, the current switches direction, but through the circuit, the direction remains the same of the current, which is why I've drawn this as swinging in the positive direction. So with these waveforms, I can find the average power drawn from the positive supply as well as the negative supply by multiplying the voltage of the positive supply with the current drawn through the positive supply, and the voltage of the negative supply times the current drawn through the negative supply. So the voltage of the negative supply is minus VCC, and the current drawn from the negative supply is minus IS negative. because IS negative is pushed into minus VCC. So the current drawn from minus VCC will be in the opposite direction. So it will be minus IS negative. So the two negative signs, they will be cancelled out, and PS negative is given as the average value of VCC times IS negative. So VCC is constant, so you can take it outside. And so you need to find the average value of IS positive and IS negative. And we can do that from this diagram here. So we need to find, so IS positive swings in this direction, like this, in the positive direction for half the cycle, and it is 0 for the other half. So similarly, the IS negative swings for half the cycle and is 0 for the other half. So we can integrate this curve from 0 to 2 pi and divide by 2 pi. Or again, integrate this curve from pi to 3 pi and divide by 2 pi. And we'll find that the average value of the two currents is the same and is given by the peak value of the current divided by pi. So VL peak over RL is the peak value of the current. So divided by pi gives us the average current drawn through the supply times VCC, which gives us the power drawn from the two supplies. So the total power drawn from the supply is the sum of these two. And it is, we divide PL, which is the average power delivered to the load, by the sum of these two. And cancelling VL and the other common terms, we get pi times VL peak divided by 4 VCC as the expression for the power conversion efficiency of the class B output stage. So from this expression, we see that if we ignore VCE sat as we did for the class A amplifier, the peak value of the load voltage is equal to approximately equal to VCC. So the load voltage then will swing from VCC to minus VCC. So the peak will be given by VCC, and when we put it back here, we obtain a maximum efficiency of pi by 4, which is about 78.5%. So like I mentioned before, the efficiency, power conversion efficiency of class B amplifier is much larger than that of class A amplifier. So it's much greater than that of class A output stage. Under this maximum efficiency, that is under this condition, when VL peak is equal to VCC, we can find the maximum power delivered to the load by replacing VL peak in this factor. If we replace VL peak with VCC, we'll get VCC squared over 2RL as the maximum power delivered to the load. Because when VL peak is equal to VCC, we get the maximum power conversion efficiency. So under this setting, the power delivered to the load must be maximum and is given by VCC squared over 2RL. So we see that unlike class A amplifier, which has a maximum power dissipation in the quiescent state. So the maximum power dissipated was equal to 2 times VCC times I, which was under the quiescent conditions. So unlike the class A amplifier, which dissipates maximum power under quiescent conditions, the quiescent power dissipation in class B amplifier is 0, because when there is no signal, there is no conduction through either Qn or Qp. There is no current flowing through RL. There is no power drawn from the sources plus minus VCC, and hence there is no power dissipated in the circuit. So the quiescent power dissipation of class B output stage is 0. We can find when the two transistors are conducting in their respective half cycles, we can find the power dissipated in the circuit, the average power dissipated in the class B output stage, by subtracting the total power drawn from the two sources. So from this total average power drawn from the two sources, if we subtract the average power delivered to the load, we'll get the average power dissipation during the whole cycle of the input signal in the class B output stage. So PS minus PL represents the average power dissipated in the class B output stage during over the complete cycle of the input signal. So this is the average over the complete cycle of the input signal. So PS is given by We have already derived it to be equal to this expression. PL is given by this factor. So subtracting this from this will give us PD, and we note that since this is the average power over the whole input, over the whole cycle of the input signal, and noting the fact that Qn and Qp, they conduct for half the cycle. That is, they conduct for equal time intervals. Q1 conducts in the positive half cycle and Qp conducts in the negative half cycle. So over the complete half cycle, for half of the duration of that cycle, Q1 conducts, and for the other half, Qp conducts. So this average power is dissipated. Half of this average power is dissipated in Qn, and the other half is dissipated in Qp. So Qn and Qp, on average, over the complete cycle, they dissipate 0.5 PD each, because they conduct for 1/2 the time interval of the full cycle of the input signal. The maximum average power dissipation in the class B output stage can be obtained by differentiating this average power dissipated over the whole cycle with respect to VL peak, and then setting it equal to 0. So differentiating this with respect to VL peak, we'll get 2 VCC over pi RL minus VL peak over RL. And when we set it equal to 0, we get VL peak equal to 2 VCC over pi. So when VL peak is equal to 2 VCC over pi, we have maximum average power dissipated in the class B output stage, where the average is taken over the full cycle of the input signal. So when we put this VL peak back into this expression, we get the maximum average power dissipated in the class B output stage, and is equal to, this is given by 2 VCC square over pi square RL. So this is the maximum average power dissipated over the whole cycle of the input signal, which means that since Q1 and Qp, they conduct for half the cycle, the maximum average power dissipated in Q1 and Qp is 1/2 this value, that is VCC square over pi square RL. So we can draw the this average power dissipated. We can plot this average power dissipated in the output stage, class B output stage, against VL peak, and this is what it looks like. So when VL peak is equal to VCC from this expression, we get the maximum power delivered to the load and maximum power conversion efficiency for the class B output stage. So this point here, it represents maximum power conversion efficiency of the class B output stage. Whereas when VL peak is equal to 2 VCC over pi, we get maximum power dissipation as we obtained from this expression. So when VL peak is 2 VCC over pi, we get maximum average power dissipation. And at this maximum average power dissipation, you can see that when I put VL peak equal to 2 VCC over pi in the expression for eta, so 2 VCC over pi will mean pi will get cancelled out, 2 will get cancelled out with this 4 here, and VCC will get cancelled out. So I'll be left with 1 by 2. So under this condition, when maximum average power is dissipated in the class B output stage, the power conversion efficiency of class B output stage is 50%, still a lot higher than that of class A output stage. So this brings us to the end of this lecture. Thank you very much for your time, and I will see you in the next class. Take care.